So we have begun to record. So again, here are today's topics for the study hall. We're going to talk about how to choose variables most efficiently in order to solve word problems. This is, as far as the advanced or basic level of these topics, this is a somewhat mid-level topic. Our discussion of weighted averages today is going to center around a shortcut for weighted averages. So this is a little bit of an advanced topic, but it's very cool. And then, looks like the last line here was cut off, just let's say comparisons. So if time permits, we'll talk about a sentence correction topic, which is the placement of helping verbs in comparisons. Couple of notes. One or two of you submitted problems that aren't, because okay, there's an email address to which you can submit study hall questions. It's on the website. I actually don't know exactly what it is, but it's on the website. A couple of you are submitting problems that are definitely not geared towards a study hall. Like a couple of people, I'm not sure if you're in the audience today or not, but a couple of people have submitted problems that are like, here's my critical reasoning score, you know, what do I do? And problems like that have their place, but that's the kind of thing you want to put on the forum or some other place where you can get a one-on-one response. Because things like that are not really study hall material, just FYI. The study hall is restricted to actually solving problems on the GMAT. So, okay. In any case, here is our menu for today, and what I want to start talking about is this, efficient choice of variables. We're going to begin that topic with a problem like this. Okay, the ratio of boys to girls in a class was originally 4 to 5. After the addition of 3 more boys to the class, the ratio is 9 to 10. What was the total number of students originally in the class? So here's what you don't want to do. What you don't want to do is to say originally boys were B and originally girls were G, and then to set up this sort of proportion where you say B over G is 4 over 5. This is what you don't want to do. Okay, because this is very inefficient. Okay, what's gonna happen with this is you're gonna have to waste your time substituting because you've got 2 variables. So you'll have to waste time getting rid of one of the variables. And on top of that, on top of the 2 variable setup, you're going to have to you'll have to use fractions. So this is really ugly. So does anybody know text box? If anybody wants to type into the text box, does anybody know how you should approach this? Does anybody know what the more optimal way is to represent this in terms of variables? You can go ahead and type in the text box. A couple of you are typing. So, okay, we got one answer where it's like just use X. So you want to stick with one variable. So what you do want to do is to use one variable. Okay, so in this case, you can use one of the techniques that's used in our strategy guide. It's what we call the unknown multiplier. So if you don't know what that means, you see the word translation strategy guide, and you'll find out all about that. But what the unknown multiplier says is when you have a ratio, you can just use a single variable if you multiply that variable by the coefficients of the ratio. So what you can do is you can say originally the boys is 4x and the girls is 5x. Okay, what it also helps to do is make a chart. It also helps to make a chart where you say boys, girls, and then you have before and after. And then this way you can just fill in the chart with the information that's in the problem. So it used to be 4x, and it used to be 5x. Okay, so then after we added 3 more boys to the class, in the text box, what expression would we fill in here for afterwards? Go ahead and type in the text box, guys. If we add 3 more boys to this class, then the number of boys after the addition is 4x plus 3. So you don't need another variable, you just work with that. And then girls is still 5x. After you have this, then you can set up a ratio with the other ratio. You've got 4x plus 3 over 5x is equal to 9 over 10. So this is an equation that you can solve. For x, you use cross multiplication and the other techniques that you would use to solve ratios. If you do that, you'll get x equals 6. And then you don't want x equals 6, though, because that's not your solution. The solution is how many students were originally in the class. And so you would type in 4x, 5x. You plug x equals 6 into that. And so this is 4x plus 5x, which is 54. Okay, I mean, you can do, I'm not denying that there is a 2-variable solution here, but you don't want to do it. Because remember, this is a very time management intensive exam. Okay, much more so than other tests you can take. You have to manage time well for this exam to work. So here's the major takeaway that you want to get here. Okay, the major lesson is if you have 2 quantities with a simple relationship, then you should use only one variable for them. Okay, this is a huge, huge, huge lesson. Any kind of simple relationship, and we'll have some more examples of this on the next page. But here's the example of the simple relationship in this problem. This is a simple relationship. Ratio of 4 to 5 is something that's very easy to do in terms of one variable, so you don't want to use 2. This is a simple relationship. So therefore, you use that to just define things in terms of one variable. And what you don't want to do is use 2 variables. Okay, so because of the time management issue, I mean, yes, you can solve the problem using this kind of approach. Yes, you can solve the problem using this kind of approach. But the major difference is that this approach is much, much, much faster. Okay, everybody give me a smiley face if you follow what is on this page. The idea that you want to use a simple relationship. Okay, we have a whole bunch of smiley faces and one not so smiley face. If you don't follow, then you can type a question into the text box and I can try to address that question. So if you were the one who gave the not so smiley face, then you can ask the question in the text box over there. And I'll try to incorporate an answer into the lecture here. So, yeah. If you put the wrong face by accident, then it was an accident. So a little bit more on this topic. Remember the major takeaway here, let's go ahead and reiterate what that is. The major takeaway is if you have a simple relationship, then you should use one variable. So here are some examples of this. And I'll have you guys respond to this in the text box. If you say something like, John and his brother have a total of $100 together. Okay, the bad way to do this would be to say J plus B equals 100, because this is two variables. It's just inefficient. I guess bad is the wrong word. It's not so much bad as it is. It's inefficient. Okay, so who can type in the text box, what's a better way to do this with only one variable? The money that John has would be what, and the money that his brother has would be what? Okay, a couple of you guys are typing it. So John is X, and then, yeah, a couple of you guys are getting it. John is X, and brother is 100 minus X. Okay, this is something you should be able to produce pretty much automatically. If you cannot instantly come up with this, then one way to help yourself train to come up with this sort of stuff is to use flashcards. So you should be able to come up with these representations very quickly. If you can't, then put them on flashcards and drill. Okay, let's look at a couple more examples of simple relationships. Okay, here's one that's like what we saw in the last problem. Let's say children A, B, and C will receive an inheritance in the ratio of 2 to 3 to 4. Okay, again, in the text box, tell the best way to do this. The inefficient way to do this is to say three variables, A, B, C, where A to B to C is 2 to 3 to 4. In the text box, what's the best way to do this? Yeah, a couple of you are answering this. The better way to do this would be child A gets 2x amount, child B gets 3x amount, and child C gets 4x amount. Couple more examples. Let's say you have driver A completed an obstacle course 2 minutes faster than did driver B. Okay. So the better way to do this would be to let driver A to be X amount of time. And then driver B, now be careful when it comes to faster. Faster, in this case, this is time. So driver A was faster, which means driver A took less time. So driver B is actually going to be X plus 2 minutes because driver B took more time. Okay, be really, really careful with speed when you get these sorts of things. When you talk about faster, in terms of speed, this would mean a bigger number. But in terms of time, the same word faster would mean a smaller number. So be really, really careful with it. Let me go ahead and space that out a little bit so it's easier to read. Okay. So here you go. Okay, again, when you talk about faster, in terms of speed, you're talking about a bigger number, but in terms of time, you're talking about a smaller number. Okay, any questions so far? And again, these are all things that you should be able to use with a single variable. and you can see how much less effort it takes once you have a single variable. It also helps to have a chart. Okay, notice in this approach that having a chart to work with is also very influential as far as an efficient solution goes. By the way, this is one thing the official guide does not really do a terribly good job of. The official guide a lot of the time uses way more variables than it should. And a lot of the time the official guide also doesn't really organize stuff the way that it could. In other words, they don't use organizational devices such as charts terribly well. But if you've got a simple relationship of any kind, then you should use one variable. So that's that. Okay, yeah, the OG is really not in the business of trying to, I mean, someone's saying the OG is trying to hose you. Well, the OG is not really in the business of helping you get better at their own test. But also, here's the same takeaway again. But, of course, now I feel compelled to also point out the flip side to this, which is if a relationship is not particularly simple, then you should go ahead and use more than one variable. In other words, don't kill yourself to try to use a single variable. For instance, if you say a hamburger costs twice as much as a hot dog, then this is just 2x and x, because this really is a simple relationship. So you should use one variable. However, if you say 2 hamburgers and 3 hot dogs together cost a total of $19, then it's okay to say 2x plus 3y equals 19, because this is not a simple relationship. So in this case, multiple variables are okay. But this is pretty much the only case in which you are all right with multiple variables, is if simple relationship just isn't happening. Okay. So any questions about this simple relationship, one variable? This is probably the single biggest way to save time when it comes to word problems. Any questions about it? Okay, smiley face if you're ready to try a problem. As a warning, the problem on the next page is not exactly the world's easiest thing, but you're a smiley face if you're ready to try a problem. Okay, looks like not too many of you are ready to try a problem, but we'll try a problem. Okay, there's some more smiley faces. So, okay, the question, there's a question in the text box. The question is, does a non-simple relationship mean unequal quantities? No. These quantities, for example, are not equal, but this is still a simple relationship. I mean, this is going to be a probably unsatisfactory definition, Eric, but it's going to be a circular definition in a way of sorts. But a simple relationship is something that you can very easily express with a single variable. Like this is something that is very easy to do. If you have a total of 100, then you have x, and you have 100 minus x. If you have a ratio like this, then you have 2x, 3x, 4x. In other words, that's actually a better definition that Sudanshu is giving here, so I'll go ahead and quote that. As far as what makes a relationship simple, you can call it an eyeball test, so to speak. But whatever constitutes a simple relationship, one of the students in here has given a pretty good definition of this. So let me go ahead and quote that. That definition is if it's easy to express the quantities in one variable, or sometimes, but not always, in terms of each other. Notice it's not always in terms of one of them. Like when you do shoe-on-shoe, if you have this situation, then this is not in terms of any one of these quantities. If you have a ratio, they're all in terms of this sort of random variable x. But again, we don't need to quibble over exactly what is a simple relationship and what's not. I mean, it's basically, if it's easy enough to use one variable, then you should use one variable. And if it is clearly difficult to use one variable, then you probably shouldn't. That's basically what it boils down to. So it's just experience. You know, you don't need 10 rules for figuring out what's simple and what's not. It's just takeaways that you get from the individual problems. Okay, a couple of you guys are typing, so I'll wait to see what you're typing, and then we'll look at problems. Okay, there's one more person typing. Okay, nobody's typing. Here's a problem. Give this a shot, and I'll put a timer on the board for you guys. Why don't you see if you can do it in 2 minutes and 29 seconds. Okay, timer is timed out, boys and girls, ladies and gentlemen. So let's go ahead and pick answers, even if that means you have to guess. What I will do, take 15 to 20 more seconds if you need it to get an answer. I'm going to start making a chart. So here's a chart. Okay, there's a chart. Okay, everybody pick something. Because again, this is the GMAT, and you do have to be able to pick answers. Again, there's some instructions over here. Please pay attention to that. Please select from the top of the left. There's polling answers at the top left of your screen. A, B, C, D, E available up top. I don't have a pointer that points that way, but they're over there. Please indicate A through E. Okay, so we've got, I'm sure there are a lot of guesses indicated here, but here are the responses that are currently shown. There they are, so I just showed them to you. I'll hide them again, and then what I'll do is I'll show you a quick bar graph of the responses. Those are people's responses. I was supposed to make a new slide out of that, but apparently it didn't. So the consensus appears to be B. One of the three answers that's none is mine, and there are two of you that insisted on not answering the problem. If you are one of these two people here who insisted on not answering this problem, be aware that that is a habit that will absolutely destroy you on this test. You must cut your losses and guess when you're done with the problem. And even if you're not done, when you get to around the 3-minute mark, you've got to just quit. But in any case, let's talk about it. Simple relationships in this problem. How many simple relationships are there in this problem? Text box, if you want to indicate. Simple relationships. Well, let's find them. This is a simple relationship. James is twice as old as Stephanie. that's a simple relationship. So let me resize my font here. Okay, this is a simple relationship. And then also, there's another simple relationship down here. So that's another one. See, here's the good thing about putting your variables in a chart, is it doesn't really matter which variable you decide to call x. But these are both simple relationships. Okay, everybody give me the smiley face if you see how these are both simple relationships. Okay, so we have a couple of options here for how to do this. So what I'm going to do is I'm going to copy and paste this onto another slide as well, so we can do this in two different ways. So there's that. Okay, so here's what we can do. Now what you cannot do is use all of this at once, because they're not in the same time frame. So 6 to 3 to 1 is not a correct ratio, as a couple of you are suggesting. What you need to do is you should use a chart like the one we have here. Schematically on this chart, here are our two simple relationships. This orange relationship is these two cells of this table. And then the green relationship is these two cells of the table. So you're not going to be able to do all of this at once. But that's the purpose of having a chart. So let's say that we decide to use one variable for this part of the problem. Okay, if James is twice as old as Stephanie, then what do you call those in the text box? Just James is twice as old as Stephanie. Go ahead and indicate in the text box what we would call those. We would call who's going to be X, who's going to be what. Go ahead and indicate, please. Okay, X and 2X. You could also say X and 1/2 X, but that is not as good because you have fractions to deal with. But here are X and 2X. James would be the 2X. Stephanie would be the X. Okay. Now, here's another key takeaway here. Another key takeaway is you should fill in as much of the chart as possible as soon as you can. So that's what we're going to do now, and that's why you should have a chart for these quantities. So if this is X, Stephanie is X years old now, then we can fill in Stephanie 4 years ago. How old was Stephanie 4 years ago? Go ahead and type in the text box, please. Correct. Stephanie would have been X minus 4. And then for very similar reasons, this would be X plus 5. And for very similar reasons, this would be 2X minus 4. And this would be 2X plus 5. Now we have another simple relationship. So even though we've already got variables, the point is we don't need another variable because Stephanie is 3 times Kate's age. So in the text box, during this time frame, Stephanie was 3 times the age of Kate. So what would this be in the text box? And go ahead and indicate, please, in the text box. Okay, yeah, you've got a simple relationship where Kate was 1/3 of Stephanie's age because of the way this works. So if Stephanie is X minus 4, then Kate is exactly 1/3 of that quantity, and so that would be 1/3 X. 1/3 X minus 4/3. So not the world's friendliest quantity, But then what you've got to do is add the 4 years. So this is 1/3 x minus. If you add 4 to -4/3, you get +8/3. And then if you need to add 5 more years here. So this is 1/3. That's a mistake. Pardon me. Okay. So this is 1/3 x. And then you add another 5, and that gives you +23/3. So now you can solve the problem. 5 years from now, the sum of their ages will be 51 years. So you add these up, and you make 51 years. So 2x plus 5 plus x plus 5 plus 1/3 x plus 23/3 equals 51. Okay, finally, people, what should be the first step of solving this equation? In order to make this as efficient as possible, yes. A couple of you are pointing this out. You really don't want to bother with things like adding 5 plus 5 plus 23/3. So in order to kill these fractions, what you want to do is you want to multiply everything by 3. So if you've got 3 times this, and you want to do 3 times this as well. And so now you've got something you can solve. So that's 6x plus 15 plus 3x plus 15 plus x plus 23 equals 153. So this is 10x plus 53 equals 153, so 10x equals 100, x equals 10. Now what I want to do is show you another way we can do this. One student is asking whether a single variable here is cumbersome. The best response I can give to that is just try doing this with 3 variables and then see how that works for you. And it's going to take way, way more time. I mean, this is not pretty, but it's not a real pretty problem. If you're writing equations for this thing with 3 variables, then you're going to have fun trying to substitute forever with that. So this is definitely the most efficient way to do this problem. Now, let's move on. Same problem, same sort of deal with the simple relationships. So let's do this. Okay, let's copy those boxes. Let me put those boxes on this slide as well. Okay. So here's what's going on now. What I want to illustrate now is that you didn't have to pick x for the quantity you're trying to find. So this is another takeaway I want to give you for word problems, which is you don't have to use the variable to stand for the desired quantity. If it's easier to use the variable for something else, then you're probably better off using it for something else. So in this case, you could have started instead with the other simple relationship. That's this one. So you could make Kate x, and you can make Stephanie 3x. Does anybody know, text box, why might that make this a little bit easier if you do it that way? If anybody knows, you can indicate the text box. Yeah, exactly. A couple of you are indicating you don't get fractions. It's the smallest quantity. So let's make a little notation of that here. Okay. So this is a good choice for the variable because this is the smallest quantity. So all you're doing is just multiplying. This is the smallest quantity in the problem. So therefore, you minimize the chances of dealing with fractions by using it as the variable. And then, of course, in some problems, you won't even use in some problems, you won't even use a variable to stand for any of your quantities. Like, for instance, if you have a ratio problem, as we talked about before, your variable isn't any of the actual quantities. It's just a random multiplier. So then we can proceed through the chart as we talked about before. Remember our golden rule from the last slide. You should fill in as much of the chart as possible as soon as you can. That's this golden rule that's down here. So as far as this difficulty level question goes, I can talk about that later, although the primary answer to that question is you don't really care. But we'll come back to that later. Okay, so you want to fill in the rest of the chart as soon as you can. This is 3x, so that makes this 3x plus 4 now because it's 4 years later. And that makes this 3x plus 9. And then this is x plus 4. And this is x plus 9. And then now you use your other simple relationship. James is twice as old as Stephanie. So you just double Stephanie to get James. So that's a 6x plus 8. That means this is now 6x minus 4. And this is now 6x plus 13. No fractions. This is really nice. So now you can add these up, and you can say 6x. Sum is 51. So that means that 10x plus 31 is 51. So x is 2. And then that's not the quantity we want. The quantity we want happens to be this one. So the answer to the problem is 10. Any questions? Okay, there's a question in the text box. Let me read this real quickly. Okay. The question in the text box is, okay, the short answer to that is no, you can't. I'll get back to you afterwards. But again, let me point out you cannot just make these 6x, 3x, and x because that's incorrect. Like this is your 2-to-1 ratio, and this is your 3-to-1 ratio. And these happened at different times. So you can't combine these ratios. That would actually be incorrect because you'd be straddling time frames. So if they were in those ratios at the same time, so the short answer here is you can't combine ratios in this problem. So, okay. Any questions about the process on this problem? Okay, as far as difficulty level, people, you really don't care about difficulty levels, especially as numbers. Like if you're worried about whether this is a 650 or 700 or 730 problem, then your priorities are in totally the wrong place. I mean, the only people that really care about that stuff are people who write tests. So make sure you keep that in mind. I mean, you should have a rough idea of whether this problem is hard for you or easy for you. But the reason you study problems is not to worry about difficulty level. The reason you study problems, as Sean pointed out in the text box, Sorry, Pierre pointed this out in the text box. See, Pierre gets exactly what the point is supposed to be. It doesn't matter how hard this problem is, because this problem is not scored. This is a study problem. What matters is that you get takeaways that you can then turn around and apply to other problems. So difficulty level is pretty much irrelevant to this kind of stuff. Okay. Any questions before we move on to the next issue here about using single variables? See, one person typing. Okay, one person is not typing anymore. Okay, we will move on. One more situation in which you can use a single variable. Besides simple relationships, you should also use a single variable when one quantity is expressed in terms of another quantity. Okay, for instance, the price of an orange is 20 cents more than twice the price of a banana. Okay, so you have an orange expressed in terms of a banana. So the price of an orange is one side of this equation, and the price of a banana is the other side of this equation. So I'm going to introduce a little terminology that hopefully won't be that hard to understand, which is, I'm going to call this the isolated variable. I'm going to call this the isolated quantity, because it's just sitting there by itself. And I'm going to call this the embedded quantity, because it's part of a larger expression. Okay, so embedded quantity. Sorry, that's supposed to say quantity. Let me change that. This is the embedded quantity because it's part of a larger expression. Okay, so everybody give me a smiley face if you understand why I'm calling these things isolated and embedded quantity. Okay, so the question is, which one of these should be the variable? If you think it should be the isolated quantity, say so in the text box. If you think it should be the embedded quantity, say so in the text box. Let's get a couple more votes here. You can even just put I or E if you want. Yeah, it should definitely be the embedded quantity. So if you have, and you guys are all in agreement on this, so this would be a pretty quick takeaway. If you have an isolated quantity, if you have a word translation that relates an isolated quantity to an embedded quantity, you should use your variable to stand for the embedded quantity. So that's the deal there. Okay, so in this case, you would use the variable to stand for the price of a banana. So X is price of banana. Because then what happens is the equation just tells you what it is. It's 20 cents more than twice the price. So that's 2x plus 20. If you try X for the price of an orange, then you're going to have a hard time doing the price of a banana without having another variable. So, like if you, let me type that out for you guys. If you try X equals price of orange, then you'll need a second variable for the price of the banana. And that's just awkward. So what the point is, you have to have foresight here. Okay, Okay, you don't just want to, I mean, another takeaway here is that you don't just want to assign the variable to the first unknown that you see. Make sure that you check out the whole problem statement before deciding what should be your variable. Okay, don't just assign a variable to the first unknown that crosses your path. Okay, so let's try a problem using this whole notion of embedded and an isolated variable. So here's a problem. Give this a shot. I don't have multiple choices this time because apparently they didn't go on to the slide. So at the end of, please don't type your answers into the box or anything just yet. At the end of time, I'll have you just type an answer into the box. So please don't call out answers. I'll have you type your answer in the text box at the conclusion of time. Okay, so here's the timer. I'll give you like 2 minutes and 22 seconds. Have fun. Okay, that's the timer. So that's 2:22. Then I'll give you another 15 or 20 seconds, and then I'll call for you to put your answers in the text box. Since we don't have multiple choices this time, if you don't have an answer, you can just put a question mark. Okay. Go ahead and type answers in the text box, please. Okay, lots of question marks. Does anybody have a non-question mark answer to this problem? Okay, so it looks like we're going to do some learning here, people. That's a good thing. A couple people are still working. Okay, I'll give you another 15 seconds if you need it. Okay, let's start here. We still only need one variable. What should the variable stand for? Let's at least go that far. In the text box, people, tell me what the variable should stand for, please. Again, if you use more than one variable for this problem, you're going to die. You don't want to use Wilsonia. Actually, no, you don't. You want to use Brownville. Shai is right. Why do you want to use Brownville? Shai or Eric, do you guys have microphones? You can type in the text box if you do. I think I'm pronouncing Shai correctly. Eric, okay, Eric, you don't have a microphone. Shai, do you have a microphone? Okay. The deal is it's this. Okay, again, if you've got it's definitely the easiest number to work with. If you've got an isolated quantity and an embedded quantity, then you could use the variable to stand for the embedded quantity. So here's the deal. In this sentence, Smithtown is 60% greater than Wilsonia. Well, okay, in this expression, Smithtown is isolated, and Wilsonia is embedded into this percentage expression. But the problem is, if you go to the next line, then Wilsonia is isolated. Brownville is embedded. So even though Wilsonia is in both equations, it's not a good choice for a variable because it's the isolated expression in this one. This one's embedded. So Brownville is the best choice for a variable. Okay, give me a smiley face if you guys understand what I'm talking about here. It's just an extension of what we saw in the last slide. And it looks like all of you understood the last slide really well. So, okay, this is the best choice for a variable. Now, okay, I'm assuming a certain knowledge of percentages on your guys' part. But, so, let's say X is Brownville. So let's put this in brown. It's Brownville. Then in this case, how do you do 40% smaller than? Text box, how do you do 40% smaller than is 60% of? So this is 0.6x. That's Wilsonia. You don't want to do times 0.4 because that's 40% of. You want to multiply by 0.6. If you have trouble with that, you can look at our FDP guide. So then how do you do Smithtown? In a text box. Notice it's not 1.6x. Because Smithtown's not 60% bigger than Brownville. Smithtown is 60% greater than Wilsonia. So it's actually 0.6, it's actually 1.6 times Wilsonia. So that is 1.6 times 0.6x. So this is 0.96x. Okay, well, Brownville has 8,000 more people than Smithtown does. So Brownville is Smith plus 8,000 people. So X is 0.96x plus 8,000. So 0.04x is 8,000. I think the easiest way to do this without a calculator is to realize this is 0.01x is 2,000. You just divide by 4. And then since that's 1/100th, you can just add 2 zeros there. So the population of Brownville is 200,000. So then you have Brownville is X, which is 200,000. You have Smithtown. You could just take away 8,000 people. So it could be Brown minus 8,000. Or you could do 0.96x. Either way, you get 192,000. And then Wilsonia is 0.6x, which is 120,000. So the total of all of this stuff is going to be 512,000 people. Any questions? Again, the main takeaway that you should have gotten out of this problem is what to pick for the variable. And notice that, I mean, most of you picked Wilsonia, but the reason why you did was probably just because it was in both equations. That's less important than this isolated and embedded stuff. If something is an isolated variable and there's another embedded variable, you don't take a variable for this one. It's harder than it has to be. So again, I mean, you can do this kind of stuff with more than one variable, but yeah. And like someone's got a 3-variable solution there in the text box that looks like it's okay to me. So again, see, the problem here is the 3 variables. It just makes you dance around the issue all day long. So, but yeah, 24/25 is 96%. So this is, you have the same thing I had, so I'm not sure what happened. But anyway, as far as why to choose the embedded variable, the most important thing is that you know that you should. I mean, you don't have to justify all these things to yourself when you're taking the test. But the reason is because if you choose this as your variable, then you have a ready-made expression for the other one. Like if you let x be the banana in this problem, then the other thing is automatically whatever this says it is. If you let your variable stand for the isolated quantity, then you're going to have to solve this equation. That's not fun for anybody. Okay. Questions? If not, we're going to change the pace quite a bit here into a cool little shortcut about weighted averages. Okay, this is sort of an advanced topic, so we're about to go on a neat little roller coaster ride here. We've got about half an hour left in the study. Okay. Someone's smiley face is stuck on. It's been flashing for about the last 20 minutes or so. It's kind of, yeah, it lends a good mood to the study hall. Yeah, we're happy smiley faces around here. Okay. Hey, well, all right. So here we go. Oh, hey, the smiley face went away. Okay, a neat little shortcut for weighted averages. Okay, here's a little build-up. I'm not just going to throw the shortcut at you right now. Instead, okay, here's an example. Let's say that let's say the room is full of men who are 6 feet tall and women who are 5 feet tall. Okay, say there are 70 men and 50 women in the room. Okay, let's find the average height. Okay, so you guys know how to compute averages and these kinds of things. So I'm going to assume that we know how to do that. So if not, then you can consult the word translation strategy guide. But the average is the sum of everyone over the count. So this is going to be the sum of everybody as you have 70 men who are 6 feet tall each and 50 women who are 5 feet tall each. And there are a total of 120 people in the room. So if you do this, you will get 5 and 7/12. Okay, what you'll get is you'll get, this adds up to 670 over 120. So I admit these are not the world's nicest numbers, but we do what we can here. So decimals you don't want. You really, really don't want decimals. Because decimals are lying to you. It's not 5.58. It's 5.5833333333 repeating. If you did use a calculator to get that, make sure you know you're not allowed to. But don't use decimals unless the problem tells you to use decimals. So this is 5 and 7/12. So let me mark that here. Okay. 5 and 7/12 of a foot. Now, let's look at a number line. Here's a number line, boys and girls. Okay, here's a number line. This is one of those things, again, pardon that it takes longer to do it on the Illuminate. But we are all models of patience here. Okay. On a number line, you can plot the following quantity. You can plot your women's height. This is 5 foot. This is the women's height. And on the number line, you can also plot the men's height. And let's plot the weighted average. So that is found right there. So 5 and 7/12. So 5 and 7/12 Okay. So 5 7/12 is our friendly weighted average. Now, here is what is cool. Okay, let's notice the following stuff. Let's notice the ratio of men to women in this problem is 7 to 5. There are 70 men and there are 50 women. So again, let's color code this just for easy reference. There are 70 men and 50 women. That is a ratio of 7 to 5. Now let's look at our number line. You may be wondering what we're doing with this number line in the first place. So here is what is very, very cool. Let's look at the distances from the average. Distances from average. This distance is 7/12. This distance is 5/12. Notice that that's the same ratio, only it's in reverse. The ratio of distances from the average for, again, men to women is exactly the opposite ratio. It's 5 to 7. The men's distance, notice you're not reading this from left to right, you're reading it men to women. So the men's distance is 5/12. The women's distance is 7/12. So this is not a coincidence. Pardon me for a second here. This is not a coincidence. It turns out it always, always, always happens this way. So that's our takeaway, and it's one of those things that spatially it's not that hard to see what's going on here, but finding the exact words to describe it is a little bit difficult. But I'm going to try. Okay, here's the result. General takeaway. The general takeaway is this. The ratio of distances from the weighted averages, WA stands for weighted average, is the reciprocal of the ratio of quantities. Oh, I really messed that up, didn't I? Quantition is not a word. This is supposed to say quantities. Okay. Quantities of these two things. In this case, it's quantities of men. I know men and women are not things, but you guys get the point. So there you go. So let me show you a sample problem here. Okay. What you can do is you can calculate, here, let me show you. Okay, let's say that, so let me give you another problem. The room is full of high school football players whose weight average is 200 pounds. And high school basketball players whose weight average is 175 pounds. If the average weight of all the players in the room is 185 pounds. What is the ratio of football players to basketball players? I mean, there are ways to do this with algebra, but we'll go into that in a second if time permits. But using this shortcut, okay, here's our number line. The number line is right here. Here's our number line. So we can plot on this number line. Football players are 200 pounds, so 200 pounds is the football players. Okay, that's football. And then 175 is basketball players. And then our weighted average is, yeah, so a couple of you are nailing this already. It's going to take me longer because I got to draw it on the screen, but I know a couple of you are starting to nail this. So 185 is the weighted average. All you got to do, because this is the quantity ratio, what we're asking you for is what we call the ratio of quantities on the last page. So the ratio, let me label that as such, the ratio of number of players is a ratio of quantities. So the ratio we want, which is number of football players, football, if you make the word football, number of football players to number of basketball players, is equal to, notice again, the quantity ratio is the reciprocal of whatever the ratio of these distances are on the number line, as long as you keep the quantities in the same order. So if we find these distances on the number line, it's just the distance for the football players, distance from basketball to average to the distance from football to average. Because again, the ratio of the quantities is the same as the reciprocal of these distances. So here are our distances. The distances on the number line, they are 10 and 15 for basketball and for football. So 10, 15. So the number of football players, the number of basketball players, is the basketball distance to the football distance. That's 10 to 15. So that's 2 to 3. And we're done. We don't have to use any algebra. We don't have to define any variables. We don't have to do anything funky at all. Notice also that if you have an intuition-based approach, you can also just realize that there have to be more basketball players because, let me go ahead and write this in the corner of the screen. Intuition-based approach. Yeah, if you think this is simple now, just wait until you see data sufficiency. And you're going to feel like you're the next, you're going to feel like you own the world when we apply this in data sufficiency. Okay, the intuitive approach. Okay, once you see the number line, you know that the ratio is either 2 to 3 or 3 to 2, if you're too lazy to keep track of the order. But you can look at this and say there must be more basketball players since the average is closer to their weight. So football to basketball must be 2 to 3. So two ways that you can do this. You can either keep religious track of the direction that you're going in, so number of football, number of basketball is distance from basketball, distance to football. Or you can just realize, I know it's 10 to 15, so I know it's either 2 to 3 or 3 to 2. And I know there's more basketball players because this weighted average is sitting on the basketball side of the number line. So there must be more basketball players. So 3 to 2 wouldn't make any sense. I mean, again, you can do this. I mean, I can show you how to do the algebra real quick, but the algebra is just sort of painful. The algebra is, you would have to say, in this case, you got to use two variables because you don't have any simple relationships. So you would say F football players, and you would say B basketball players. So you would say the average weight of all the, so the average weight is F times 200 plus B times 175 over the total number, the total count of players F plus B, and that equals 185. Okay, I mean, I don't want you guys to sit here in a study hall and watch me do algebra, but if you solve this, you'll eventually come up with F over B is equal to 2 to 3. That's a mistake on top. That's a mistake. Nobody saw that. Bye-bye. Okay, the correct ratio is 2 to 3. This is what you'll get if you eventually do all this algebra. I mean, I don't want to sit here in front of you guys and do algebra, but this is what you'll get. But this sucks. Okay, let me give you a nice unhappy face because that's just not as nice. And then here's the kicker. If you guys don't realize what good news this is already, wait until you hear the following. If this is a data sufficiency problem, if this were, I didn't give this to you as a data sufficiency problem, but if this were a data sufficiency problem, where it was like, what is the ratio, then you'd be done as soon as you see this and this. Let me show you what the thises are. As soon as you see this orange highlighter, and then as soon as you see this stuff on the number line, you're done. You don't have to do anything. You don't even have to find the numbers. Like, because you just know, you know that you can find the ratio, and that's it. That's enough to be sufficient. End of story. You can pick. So this is beautiful because what I've seen is most of these actually show up on data sufficiency, and so there's actually a higher chance than not that you'll be able to just kind of, you know, finish the problem nice and quickly and then kind of chill and smoke an imaginary cigar while everyone else is scrambling to give you algebra. So here's a problem. Try your hand at this. This is from GMAT Prep. I'll still give you 2 minutes to do it. But if you have a grasp of what we're talking about here, you probably won't need that much time. But again, you will have polling A through E answers. Go ahead and indicate A through E at the top left of the board, as you did before. Okay, ladies and gentlemen, that's 2 minutes and 1 second. Go ahead and indicate an answer in the text box, please. Not text box, sorry, not the text box. Top left of the illuminate window. There are polling choices, A through E. Okay, so we are starting to wind down the time here. We've only got about 10 minutes left in this session. So let me just give you a quick summary. Most of you have this, but let's look at statement 2 first, because statement 2 we can dismiss pretty quickly. Average is sum divided by count. So in this case, we have the sum, but we don't have the count. So that's not going to work. So this is, if you use our chart, our grid here, BD is probably the easier way to go here. So this is not going to be sufficient. There's 2 people who mark D, so just make sure that you follow this argument. You can also realize that if you have an intuition about these sorts of things, we don't know how many people there are. I mean, N is not a number. So if you have lots and lots of people, and this is all the sum of their heights, then they could be very short. But if you have few people, relatively speaking, then they could be very tall. So, okay, let's look at statement 1. The key thing that you have to notice here is that this is N thirds. So this is exactly 1/3 of everybody. That's the key point. So you have a quantity ratio. Let's see, the question is, the numerator equals 178 why don't you send me, Sean, why don't you send me an email with that question later? I'll probably post my email address at the end of this session. The short answer is no, because that's not sufficient. But as far as the reason why, I can clear it up on email. Okay. Anyway, so the statement is quantity ratio. So this is, let's just call them tall people and short people. So tall people constitutes 1/3 of the group, and short people constitutes 2/3 of the group. So this is therefore a 1-to-2 ratio of tall people to short people. And I know 5'10" is not really short, but you know what I mean, relatively speaking. So, all right, that's a 1-to-2 ratio of taller to shorter people. So let's put this on a number line. Here's a number line. In this case, we have here are the pure statistics. We have a 6 foot 2.5. So this is 78.5 inches. Sorry, this is 74.5 inches. And then this is 5'10" is 70 inches. And then your weighted average, now see, here's the deal. If you've got this 1-to-2 ratio of taller to shorter people, then that means the ratio of the distance from taller to average to the ratio of the distance from shorter to average must be 2-to-1. So that means you have to be dividing this number line up into a 2-to-1 quantity. So where it's 2-to-1 taller to shorter, so that's going to be backwards as far as the number line is concerned. So you know this is a ratio, so you can use that fact to realize that the taller people's distance is, sorry, that's backwards. I'm going to erase that. Actually, I can just move this. This belongs over here. There you go. Okay, that's been moved. All right, the taller people's distance is 2x, and the shorter people's distance is x. So you know you can find this. So that's sufficient. Again, you can also do this with algebra, but that's not the point of this unit of the study hall, is to show you algebra. Okay. Any questions about applying the shortcut to this problem? Yes, there is an algebra solution. No, we don't have time to do it right now. But are there any questions about this? Okay, thank you. Let's close out with one more problem, which is going to be this one. Give that a shot, please. Same deal, A through E answers indicate. Here's your timer. Here's your timer. Okay, people, ladies and gentlemen, let's go ahead and pick answers. Here in the twilight of this particular session. Okay. Everybody pick something, please. There's about 3 or 4 of you that don't have. This problem, by the way, is an absolute nightmare with algebra. Okay, so if Brunel, if you're there, and Sandy, if you're there, go ahead and pick something from A through E, please. Okay, apparently those 2 people are not responding. So let's show the, here's the answers. It looks like we're deadlocked between E and C here. Here's what we're looking at right now. So here's the story. Okay. If you look at statement 1, let's look at number lines. Because again, it's what percent. Okay, so one thing that's a takeaway here is if you don't realize it. This is the same, in a data sufficiency problem, this is the same thing as asking for the ratio of managers to directors. Or for the fraction of directors, or for the percent, or for, whatever. So because any of those you can get from any of the other ones. So, for example, if there are, like for instance, the FDP strategy guide will help you remember how to do this if you don't remember how. But if you can always go back and forth between things like fractions and ratios. So if you have, like, for instance, if you had like 2 to 3 managers to directors, would mean that there were 2/5 managers, would mean 40% managers, etc. I mean, all these are equivalent. That's not the answer. It's not 2 to 3. But the point is that this is a really key takeaway. if they ask you what percent, you don't have to break your back to find the percentage, because all you have to do is just find the, you can find a ratio and you're good to go. So let's look at statement 1 here. Statement 1, here's a number line. Statement 1 is like this. Okay. Here's our managers. Here's our directors. This is not to scale, because I'm going to use the same diagram for all of these. So the average salary, the directors is 15. All right, I'm going to do a little copying and pasting black magic here. So just a second, guys. All right. Let's drag this down here. And then, wait a minute. Whoa. Let me do that. Okay. Sorry, we got to do that again. Okay. I messed that up. Now, here's a number line. No sound effects. Guys, believe me when I tell you that I do not know my way around a computer to save my life. So, I'm doing what I can here, fellas. So, okay. Here's something for you. Let's move this down here, and then, why does it keep doing that? Okay. Drag it down here, and then we'll copy it again. And then we'll drag it down here, and then we'll copy it again. Okay, that's all I was trying to do. Okay, statement 1 is going to look like this. Statement 1, you've got a weighted average, managers, directors, weighted average. It's 5,000 less. So we know that this distance here is 5,000, but we have no idea what this distance is. Notice I switched directors and weighted average. Weighted average is, pardon me, people. This is the weighted average over here, and this is the directors over here. Okay. Notice that directors does have to be more, because it's impossible for both of them to be less. So there you go. That's insufficient because we don't know what this ratio is going to be. I mean, it's not only if we know this ratio, then we know the quantity ratio, but if we don't, then we don't. In statement 2, we don't know what this distance is, but we know that this distance is 15,000. That's still insufficient, though, because we don't have a ratio. In this case, if you have them together, then the weighted average is, this is 5,000, this is 15,000. So this is sufficient. Again, you don't have to do the work, but notice that the quantity ratio is the inverse of these distances. So number of directors to number of managers is the ratio of managers to directors on the number line. That's 1 to 3. So, yeah, I mean, the number of them is independent of what they're paid. That's correct. But when you have this sort of situation, I mean, the way to think about this intuitively is, I mean, I think you guys who are asking this question, again, I've got about 2 minutes before I gotta log off, but I'll do my, because we're 10 minutes over already. But I'll do my best to explain in 2 minutes here what's going on. I think if you're just handicapping, I mean, I think you're handicapped by just thinking about formulas and not trying to think intuitively about this. If you think intuitively about this situation, you've got this situation going on here. Yes, I mean, you can pay them whatever you want independently of how many there are, but the fact that the weighted average is precisely this close to managers versus directors is why you've got to have a certain number of people. Like Sean Shy, you guys who are asking this question, if you had way more managers than directors, like if you had 100 managers and only 1 director, your average would basically be right here. If you had 100 directors and 1 manager, then your average would be basically right there. All right. So the fact, this is why this works the way it does from an intuitive standpoint. If you had 0 managers, then your average would just be whatever the director's average is. So the point is that's why this shortcut works the way that it does. If you're exactly this fraction of the way down the line from managers and directors, then that fixes the ratio of those two. If that doesn't intuitively make sense to you, you still have the option of memorizing the shortcut. So, okay. All right, people, I've got to go. We're 10 minutes over, and unfortunately, I don't have time to answer any questions. But if you want to shoot me a quick question or two, here's my email address. I put it in the text box. Sorry. There's my email address. So if you have quick questions, you can shoot them to that email address. Otherwise, you guys can quit out of this room. You can just close the entire application. You don't have to do any sort of special procedure to quit. You can just quit the entire application. Otherwise, I'll go ahead and start kicking people out here in the next like 30 seconds and close the window. So you've got the email address, you know what to do. Have a good night. As far as future schedule, we're still going to nail that down. I don't think we have a hard schedule yet, but we will certainly, we'll certainly let you know, and we'll post it on the website and all this other stuff. And whatever forums that we notify on, Beat the G-Men and so on, we'll do that too. Okay, guys. Again, we're over by 10-15 minutes, so let's knock it out and have a great holiday, and I will see you guys later. Yeah, don't be a douchebag. Yeah, don't be a douche, dude. Well, don't be a douche. Don't be a douchebag. Don't be a douchebag.